Okay, let's have a look at this question then. The first question is asking, what do we mean by the wave-particle duality, and in this case it's of electromagnetic radiation? Well, the wave-particle duality of EM radiation is simply that electromagnetic, and do not abbreviate this in the exam, radiation can behave as either a wave or a particle. Okay, that is the definition of the wave-particle duality of electromagnetic radiation. The next part, and if you notice there are only 2 marks available for both of these parts, so you'd be looking at getting 1 bit of information for both. Which aspect of the dual nature of the EM radiation is demonstrated by the photoelectric effect? Well, we're dealing with photons, packets of energy, and so it is dealing with the fact that EM radiation behaves as a particle. Then if we go down to the next part, we're told that a metal plate is illuminated with UV radiation and they give us the frequency. We're also told that the electrons have a maximum kinetic energy and these electrons have been liberated, and that means instantly we know that the energy, E equals HF, of our photons must be greater than the work function of the material, and we know it must be greater and not greater than or equal to because the electrons have got extra kinetic energy. So, the energy of my photon is going to equal, if it's been successful in releasing photoelectrons, the work function of my material, and any extra energy left will manifest itself in the kinetic energy of my electrons that have been released. Now I can rearrange this to get it in terms of the work function. Okay, the work function is going to equal my HF, and I take my kinetic energy to this side, so it becomes minus KE. Now my kinetic energy I have, my frequency I have, and I know that H is equal to 6.63 times 10 to the minus 34. So I can plug all of this into my equation to get my work function. 6.63 times 10 to the minus 34 times my frequency, which I was given up in the question. Stick that in a bracket, minus my kinetic energy, which was 3 times 10 to the minus 19. And when I plug all of that into a calculator, I get a work function of 8.1 times 10 to the minus 19. And don't forget your unit, a work function is an energy, so my unit is joules. Then we're told that the radiation is maintained at the same frequency. If it's at the same frequency, then we know that the energy is going to remain the same. So if it released photoelectrons beforehand, it'll still release photoelectrons now. But this time, it's doubled the intensity. Sorry. Now, what effect will the intensity have? Well, it doesn't affect the energy because there's no intensity term in there, but it does mean that we need to think about the number of photons hitting the plate per second. If you double the intensity, you double the number of photons, and since each photon has got enough energy to release an electron, you would double the number per second being released. However, the intensity has no effect on the energy, so there's going to be no extra energy to give the electrons, so there'll be no effect on the energy of our released electrons. And finally, this time we replace it with another metal plate of a different material. It's illuminated by radiation of the same frequency, but this time no electrons are released. Why does this happen, and what can we deduce about the work function of the new material? Well, we can see instantly that electrons do not have enough energy to escape the surface of the metal. This tells us that the work function of the new metal is greater than the HF, or the energy of the photon that are bombarding the surface of the metal. And so, since last time electrons were released and this time no electrons are being released, we can deduce that the work function of the new metal must be greater than the work function of the old metal. And there we have it.